Hi everyone, and welcome back to video 3 of your snow day lecture. And so where we left off is we were talking about this idea of using epoxides as a way of doing substitution type reactions. And we were using under basic and neutral conditions and a strong nucleophile, we could crack these suckers open to create a carbon nucleophile bond and a new alcohol. Where I want to focus on now is what happens when our epoxide here winds up being asymmetric, when there are two different places that our nucleophile can attack. What do we do in terms of regiochemistry? And so remember, regiochemistry simply refers to the region of the molecule in which we are adding our functional group or our reaction is taking place. And so it turns out that these types of epoxides are able to be substituted in different ways. And so the example I've shown here has two different carbons, one of which is a primary, and the other which is a tertiary. And remember, tertiary and primary simply refer to the number of carbons that are attached to it. This guy has 1, and this guy has 3. And so because these are primarily SN2 reactions, what we need to keep in mind is that sterics wind up playing a very important role. The less substituted the carbon that's undergoing backside attack, the faster the reaction. And this is just simply a steric consideration. Our nucleophile is going to have an easier time accessing the LUMO of a carbon-oxygen bond with the fewer amounts of stuff to get through than something like this tertiary carbon-oxygen LUMO, simply for the fact that there's a lot of methyl groups you've got to get by before you can overlap those frontier molecular orbitals. And so, generally speaking, under basic or neutral conditions, nucleophiles will preferentially attack the less substituted side. So for example, when we're taking a look at this, what we can do is we can add a strong nucleophile, and so something like methyl magnesium bromide, this is a Grignard reagent. We can add this to our asymmetric epoxide. And what we'll do, doing this so it stays in the camera strap, we'll mix these together in some sort of solvent that is polar aprotic. When you're dealing with Grignard reagents, typically the solvent has to be in THF or ether, something polar aprotic and ethereal. So we'll use THF in this case. So we'll mix them together in THF and then add acid in the end. And so what we're going to primarily get is we're going to get our nucleophile attacking the less substituted side of our electrophile, the epoxide here. And what this will wind up doing is it'll wind up cracking open our ring. O minus. And so we'll just pretend that we haven't added the acid yet, so I can do this stepwise. And in doing so, we've created our carbon-carbon bond away from our more substituted position. And in the end, so that we get the neutral alcohol, we'll have to add just a smidge of acid. Typically HCl is a great way to go. But H2SO4, any dilute proton source, usually aqueous, is really the way that these reactions wind up working well. And so you can just envision that alkoxide pulling off that proton. Generating this type of alcohol species here. An important thing to remember is that when dealing with SN2 type alkylations of epoxides, this is truly an SN2 type reaction. And so because of this, we need to be cognizant of the fact that these types of reactions will occur with stereochemical inversion if they occur at a chiral center. And so let's just remind us of ourselves that in our notes. Okay, so let's give this an example of what we would see if this was happening at a chiral center. So what I would like you to think about is that we're taking some sort of chiral epoxide. I'll make one side tertiary so we can block that side. The other side, what I'll say is we'll give this a methyl group coming out. Okay? And so, this is a hydrogen. If we then add some sort of alkoxide, so imagine as a strong nucleophile, we're adding NaOMe. This is preferentially going to attack the less substituted side over here, but it's going to do so in a manner of backside attack that's going to invert this stereocenter. So if we look at this stereocenter here, we have a chiral center, and so dealing with this, our lowest priority group is to the back, almost like I planned it. So so this will wind up being 1, 2, 3. So this is an R stereocenter. And when we go ahead and do backside attack, especially when our incoming group is the same as our leaving group, we're going to invert that stereocenter. So specifically, backside attack, this sucker is going to crack open. And we're going to create our alkoxide species here. Again, you want to add a little bit of acid to make sure you make this neutral. You can pick your favorite acid in this one. Let's make it, I don't know, let's make it ammonium chloride this time. You'll see that quite a bit. We'll pull that sucker off. And what we can see is now we're left with this chiral alcohol here, and what we're able to do then is we're able to look at its absolute configuration. So again, our lowest priority group is still at the back. 1, 2, 3. This winds up being S. And so just a reminder that anytime you do have this SN2 type chemistry, you are going to be dealing with stereochemical inversion. So where we're moving next time in the next video is we're going to look at these epoxide opening reactions under acidic conditions and how they can differ in the types of products that we can form and the regiochemistry of the products that we wind up producing. Okay, see you soon.